Hey there, how's it going? This video, what we're going to be taking a look at is how to determine the area and arc length of something in polar form rather than rectangular form. Now, we've seen arc length previously. We've seen arc length previously in BC calculus, where in rectangular form, we said that the length of the arc was equal to the definite integral from a to b of the square root of 1 plus the derivative f prime of x squared. So we've seen how to find the length of an arc, at least in rectangular form, and now we're going to do something similar in polar form. And I don't know what happened here. Clearly the L is not in the same font as everything else. Let's continue our investigation of polar curves related to areas and arc length. So there's a little bit of information that I want to make sure is clearly identified here. All right. When finding, where am I at? When finding areas in regular rectangular coordinates, we use rectangles to approximate the region. Okay. Well, in polar coordinates, we will use sectors of circles. Another small change will be in our language. In rectangular equations, we found the area under the curve, but with polar equations, we will find the area enclosed by the region of the polar curve. Effectively, it's the same thing. I don't know, but it's a vocabulary thing. What do you want me to say? I don't know why they did it that way. That's just what they did. Why is a wall or the floor on a boat different than a wall or a floor anywhere else? Instead, it has to be a bulkhead or a deck. I don't get the vocabulary. I don't get why it is what it is. I just know that's what it is. So let's see what we have here. The polar area concept. Now, depending on what you have seen previously in mathematics, we've seen sector area ideally in one of two, possibly two different classes. So here, this is representing like a central angle. And what I have here is just the sector of a circle. Okay, and the sector, maybe you can think of it as, I don't know, like a region of a hard drive or whatever, but this is maybe a slice of a pizza that you're going to take, but that's the sector area. And what we've done previously in math to find the sector area, the way I like to do it is I teach it as a proportion, where I say the sector area is a ratio of the entire area, which is just pi r squared of a circle, is equal to the central angle, which we're calling theta in this case, divided by the total number of degrees of a circle. And that's how I teach it whenever I teach geometry and we're doing sector areas or just, or even arc length of a sector in circles. There's another proportion that we use. But in pre-cal, you may have seen the same thing. And if I take, or at least the same concept as far as finding a sector area. So in pre-cal, you might have seen, something that I'm going to take the geometry formula and I'm going to rearrange it a little bit. What I'm going to do is theta is going to stay the same, but in pre-cal, you start really getting into a radian measure. So a radian complete circle is going to be 2 pi. And if I want to rearrange that to actually just have the sector area by itself, we can say the sector area is equal to pi r squared times theta over 2 pi. And you can see that here the theta, pi and pi simplify. And so I would say that the sector area is effectively 1/2 times the radius squared times whatever theta is. And that's basically what we're going to be talking about here is we're going to kind of use that idea to now find the same thing, but now with calculus and polar functions as opposed to anything that would be rectangular. And I approached that idea similarly to what we have seen in other math or in other areas in this course. When we first introduced the idea of a pole or of the area under the curve, we first introduce it with the idea of Riemann sums, where if I draw a whole bunch of kind of rectangles underneath the curve, we can approximate the area under the curve by adding up the area of the rectangles. And if we had an infinite number of rectangles contained between the 2 points of the interval that we had, then that's where we really introduced the idea of integration. Well, we're doing the same thing with a sector area. Now, not everything that we're going to see with our polar coordinates are going to be circles. We're going to have weird looking curves in some cases. Some are going to be pretty to look at. Some are going to be like, that looks kind of weird. But we can approach it with the same idea that we did with rectangles in Riemann sums and apply it with sectors with Riemann sums, where if I have an infinite number of sectors, we can find the area of the overall sector of the, polar function, whatever it happens to be, from one part to another part. In this case, where when horizontally with Riemann sums and rectangles, we would say delta x for maybe the height of the rectangle. Here we're going to have delta theta, the change in the angle from alpha to beta in this case. So what does that mean? How are we going to be what are we actually going to be working with? Well, the integration that we ultimately end up with, here where they're saying f is a continuous non-negative on the interval from alpha to beta, then the region bounded by the graph of r is equal to f of theta between the radial line that's going to make an angle theta and then another angle beta from the x-axis is given by the area to be 1/2 of the definite integral from alpha to beta of either the actual function that they give you squared, or we can simplify that and just say the radius squared. And this is going to bring us to our first example. Okay. Now I'm going to be clear, those of you that are following along with this for all of the examples, there are going to be some integrals that we're going to wind up getting that are really going to just be too complicated or too time consuming or too tedious to try and figure out what the value of the definite integral is going to be. So in some cases we will use a calculator to figure out the approximate value of the definite integral, but in other cases we will use just our normal antiderivative techniques, and there's some things that I want to make sure that you see. Now here, this one is called a cardioid because it kind of has, horizontally, if you turn your head to the left a little bit, you can kind of see how it kind of this part here and this part here kind of looks like the top of what we would, typically think of as a heart. So that's why cardiology, cardiovascular, heart, cardioid. Anyway. Cardioid, remember, is made when the A and B values, those ratios, when the absolute value of B to A is equal to 1. That's what creates the cardioid in 1. If the ratio was less than 1, that's what creates those inner loops on the limacons that we have seen previously. So find the area of the cardioid. Now in this case we're not looking for a particular sector, we're looking for the entire thing. So the only way that I can get the area of the entire thing is if I go from 0 to 2 pi. It's the only way I can get the whole thing. And that's what we're asking for the area of, is the whole thing. So what do we have? We have the area is equal to 1/2 times the definite integral from alpha alpha to beta of r squared d theta. Well, in this case, r squared, of course, is just, this is f of theta. So that's what we have to substitute no matter which version of what we saw here. You know, so I'm going to say area is equal to 1/2 times the definite integral. In this case, we know now we're going to go from 0 to 2 pi. And I'm going to say 1 plus cosine of theta squared d theta. So we're going to go ahead and try and expand that and see what we can wind up getting to simplify this a little bit. So I'm going to wind up with a is equal to 1/2 0 to 2 pi. And if I expand the binomial and distribute everything, we're going to wind up with 1 plus 2 cosine of theta plus cosine squared of theta, all of it with respect to theta. Now, one of the things that I'm hoping that we're going to be able to start recognizing, and this is part of the reason why I want to make sure that I do this one without a calculator, is the cosine squared of theta. That is, this is one of our power reducing formulas. Okay. This is something that we see with some of our advanced integration techniques when we're working with trig stuff. And the cosine squared of theta is either equal to 1 plus cosine of 2 theta over 2, or you can write it as 1/2 1 plus cosine of 2 theta, whichever you prefer. So let's keep going here. And the reason why I want to do that is because cosine of 2 theta is going to be easier to integrate than cosine squared of theta, because there's not going to be any real opportunity for me to be able to create a trig identity with a sine squared plus cosine squared. So let's see what we get here. So I'm going to say 0 to 2 pi. So I'm going to write this as 1 plus 2 cosine of theta. And I'm going to write this one here as 1. No, I want to write it as 1 plus cosine of 2 theta over 2. If you prefer the 1/2, that's fine. And boy, that's like the ugliest 2 I think I've ever written. 2, there we go. All of it with respect to theta. So now I am going to go ahead and start taking the antiderivative of everything. So I have 1/2. The antiderivative of 1 in this case will be 1 theta. The antiderivative of 2 cosine of theta is going to be plus 2 sine of theta. Here with the fraction, we're going to have 2 parts. We're going to have the 1/2 that we have to do the antiderivative of, so that would be plus theta over 2. And the cosine of 2 theta over 2 is going to be, that is going to be a negative sine of 2 theta over 4 d theta. Nope, not d theta. I'm not doing integration anymore. Or I'm not writing the definite integral anymore. I'm doing the antiderivative. So we're going from 0 to 2 pi. Now normally if I have my lower bound of my antiderivative to be 0, I like it because usually it means we're going to wind up with 0. but that's not always the case with trig stuff. So let's go ahead and start doing this. So I'm going to just make one big substitution here with my fundamental theorem of calculus. So theta becomes 2 pi when I substitute it first. So I'm going to say plus 2 sine of 2 pi plus 2 pi over 2. Nope, not plus, minus. Minus sine of 2 theta would be 2 times 2 pi, so it'll become sine of 4 pi over 4, and that's the upper bound stuff, and I want to have that all in one thing. And now I'm going to subtract the lower bound stuff, so 0 for just theta, and then we're going to say plus 2 sine of 0 plus 0 over 2 minus sine of 2 times 0, so that would just be sine of 0. Let's just say sine of 0 over 4. So there's the lower bound, and there's the upper bound minus the lower bound contained inside of the brackets. Let's see. So here, sine of 2 pi is just going to be 0. So 0 times 2 is just 0. 2 pi over 2, that's going to just simplify to be pi. Sine of 4 pi is basically sine of 2 pi, so it's just going around twice. So all of this whole thing is going to go to 0. Of course, 0 is 0. Sine of 0, y is 0, so that's going to be 0. 0 over 2, of course, is 0. And sine of 0 is going to be 0, so 0 divided by 4 says that's going to go to 0. So we do have quite a lot of things that kind of drop off here. So what I'm left with is I have my 1/2. I have 2 pi plus 1 pi, so that'll be 3 pi. Everything else is 0. So my area in this case is going to be 3 pi over 2. And there's my area of the cardioid. And that one particularly, I wanted to make sure that we did by hand because of the power reducing stuff for the cosine squared theta. And the next one is going to be another one. This is going to start to challenge the limit of what I think would be possible, maybe on a free response question without a calculator as far as your time is concerned. Here it's asking us to find the area of one petal. Okay, so this one, you know, how are we going to think about this one? Well, first of all, what's my interval going to be? Now, I don't know. In the notes and in the presentation here, we just have one petal, which is fine, but I don't see why we need to have that second graph. We're just finding the area of one petal. So we're finding, let's just focus on this guy right here, I guess. Okay, what's the area of that petal? Well, I need to know what the interval is going to be. We know what R is, so we know what we're going to be using for our interval when we, or for our R value when we do our integration. But what's the interval going to be? Okay, so what I'm going to do to find the interval, now you can find the interval in this case one of two ways. And the first way I'm going to show you is going to be an algebraic approach. To find the interval, set R equal to 0 and solve for theta. So basically what I'm going to do is I'm going to just take 0 and substitute it wherever I have an R, and I'm going to have 4 times the sine of 3 theta basically is equal to 0 when I substitute 0 for r. So divide by 4, and that'll just give me sine of 3 pi is equal to 0. So where does sine actually equal to 0 at? Well, sine is going to be equal to 0 at 0 and at pi on our unit circle. So if I say 3 pi or 3 theta is equal to 0, then that means theta is going to be equal to 0. And if I say 3 theta is equal to pi, then theta is going to be equal to pi over 3. So that's algebraically how I'm getting my interval. My interval now is going to be from 0 to pi over 3. Did I need to do that? Not necessarily. If we remember the angles on our polar graph here, obviously this is state 0. This first dotted line right here is pi over 6. And the next dotted line that we get is pi over 3. So the interval that petal is contained between is between those two angles. So that's graphically how we could have identified what the interval was going to be. It was from 0 to 2 pi, or I'm sorry, 0 to pi over 3. So graphically, sometimes it's going to actually be pretty difficult to figure out, but in this case, it was easy to kind of just see what they were going to be, but that's how we have our interval. So now let's go to our area now and see what we have for our area. So I'm going to just go ahead and, because I know I'm going to take a lot of space horizontally the way I'm writing. So I'm going to just go ahead and take all of this stuff here, and I'm going to clear it off so that way I have space to do my area. So area being equal to 1/2 of the definite integral from alpha to beta of r squared d theta. Doing my substitution here, we've established the definite integral is going to go from 0 to pi over 3. And the radius that we're working with in this case is 4 times the sine of 3 theta. Okay, so if we square it, we're going to wind up with 1/2 0 to pi over 3 of 16 times sine squared of 3 theta. Okay, and here again, what we're hoping to recognize, part of the reason, one of the main reasons why I want to do this one by hand here, is that sine squared of theta part. This is our, again, this is our second power reducing formula. Which in this case, we have sine squared of theta is equal to either 1 minus cosine of 2 theta over 2, or 1/2 of 1 minus cosine of 2 theta, however you want to work it. So in this case, I think I'll go ahead and do this one because I did the common denominator fraction on the previous problem. So let's go back to finding our stuff here. So let's see. Area is equal to 1/2 definite integral 0 to pi over 3 The 16 is not affected by the power reducing formula, but in this case, I'm going to wind up saying, or actually, you know what I'm going to do? What I'm going to do now, let me go to another color real quick. I'm going to go ahead and pull this 16 out as a constant. Okay, I'm going to pull that 16 out as a constant. So instead of saying 1/2, I'm going to say half of 16, which in this case will be an 8. And then, so now I can just focus on the sine squared of theta stuff in the integral. So I'm going to just say the 1/2 by the power reducing formula times 1 minus cosine. So here I have 2 theta multiplied by 3. So that's going to wind up to be 6 theta here. And d theta. So one more time, I'm going to go ahead and pull out this 1/2 as a constant when I move to my next step. So half of that 8 will be 4 times the definite integral of 0 to pi over 3. And that's just basically going to be 1 minus cosine of 6 theta. And looking at this part here, what I really think I want to do is I want to focus on what can I do with just the cosine. So I think at this point here, I'm going to use my properties of integrals. And I'm going to say we have 4, and the properties of integrals that we're going to wind up getting is I'm going to just separate those two from each other. And I can say the definite integral of 0 to pi over 3 of 1 d theta minus the definite integral of 0 to pi over 3 of cosine of 6 theta d theta. And that's going to be a lot easier to do some integration with. And so let's see what we get. In this case, I'm going to look at the integration that I have on the right. I am going to do some U-substitution here, where I'm going to say U in this case is going to be the 6 theta. So the derivative of that will just be 6. So du would be 6 d theta. So I'm going to have 1/6 du. So I'm going to have a constant of 1/6 being introduced in front of the integral of just d theta. And because I'm doing u substitution, in this case, when u is equal to 0, nope, when theta is equal to 0, u will be 6 times 0, that's just 0. And when theta is equal to pi over 3, well, 6 times pi over 3, that's going to be 2 pi. So we have 4 ultimately as a constant that was pulled out. So I'm going to have I'm not going to do any anti-differentiation just yet. So I'm going to have just the definite integral of 0 to pi over 3 of 1 d theta. Now here, when I subtract the second integral, we did have a constant of 1/6 that got introduced. My upper and lower bounds don't get reversed, but they change from 0 to 2 pi cosine of u du. And now this is where I think I can go ahead and start doing some anti-differentiation. So the antiderivative of just the 1d theta, that's going to be theta evaluated from 0 to pi over 3 minus the 1/6, the antiderivative of cosine is just going to be sine of u evaluated from 0 to 2 pi, and all of it multiplied by the constant of 4 that we took out. So let's see what we get. In this case, substituting here with 0 doesn't matter, so that's just going to be 4. Substituting with 0 doesn't matter on that first one, so that's just going to be pi over 3 and minus the 1/6, and in this case substituting either 2 theta or 2 pi or 0, sine of 2 pi minus sine of 0, those are coterminal 0, not theta. 0 and 2 pi are coterminal angles, and both of those give me sine to be 0, so this whole thing simplifies to be 0. So 1/6 times 0 is just 0. So I have 4 times pi over 3, which would just be, and I forgot writing my area. So area is 4 pi over 3. And there we go. So one petal is 4 pi over 3 square units. Now this next one here that we're going to be looking at is again a similar kind of idea of what we were looking at this one. Here it kind of looks like the infinity symbol of r squared is equal to 9 cosine of 2 theta. And in this case, you know, this is almost like what a rose would be, but in the, you know, we wind up with just the kind of like this infinity looking symbol here in this case. And it's asking us again, what's the area inside of one loop? So I am going to focus on the loop on the right, because that'll give me positive kind of thetas or x values, whatever you want to think of it as. I'm going to focus on that side right there. And in this case, I'm looking at it, and I want to say that I'm using maybe this angle and this angle, but it's a little hard to tell on the graph that we have what they're going to be. They don't exactly look like they're exactly tangent to the curve, so I definitely want to make sure that I can figure out what the interval is going to be here. So what I'm looking at, this is my thinking. This graph makes it hard to see what angles are used. So kind of like what I did on the last one. Set r equal to 0 and solve for theta to get the interval. So that's what I'm going to do first. In this case, r is 0. 0 squared is still 0. So 0 equals, what do we have? 9 cosine of 2 theta. So let's solve. So divide by 9, and 0 divided by 9 is still 0. So now I have cosine of 2 theta. And again, cosine is where we're dealing with x values. So the principal values for cosine that we might be working with are only going to be in quadrant 1 or quadrant 4. So in quadrant 1 of our unit circle, cosine of theta is going to be equal to 0 at pi over 2. And in quadrant 4 of the unit circle, cosine of theta is equal to 0 at negative pi over 2. So if I take the 2 theta and I set it equal to positive pi over 2, dividing by 2 gives me theta to be pi over 4. And doing the same thing with the negative pi over 2, negative pi over 2, that will result in theta being equal to negative pi over 4. So that's my interval. My interval is going to be from negative pi over 4 to positive pi over 4. So that's my interval, and that one wasn't very easy to determine by looking at the graph in that case, because the closest dotted lines that we had looked to be about positive and negative pi over 3. So that didn't work out to be the case here. Now in this particular problem, it will be simpler, I believe, to double the interval and go from 0 to pi over 4. I'm going to use the symmetrical nature of the figure that I have here, and I'm going to just go from 0 to pi over 4, but I'm going to double my interval. So that's what I'm going to be looking at here. Now again, I hope you have this copied down, because I'm going to erase it so I can use this space to find the area. So here, instead of saying what I'm going to have is I'm going to have the, oops, turn my pen back on. I'm going to have the area. Now I'm doubling my value, so 2 times 1/2 times the integral from alpha to beta of r squared d theta in this case is going to result in the area being equal to the definite integral, because 2 times 1/2 is just going to simplify to be 1. In this case, from 0 to pi over 4 positive. And we're going to take r squared is already given to us to just be 9 times the cosine of 2 theta. We don't have to figure that one. We don't have to actually do anything on that one. It's already squared for us. So now that I have that, I'm going to pull the 9 out as a constant, so that way I can just focus on cosine. So here I'm going to say 9 times the definite integral from 0 to pi over 4 of just cosine of 2 theta d theta. And like I did on the last one, at this point, I'm going to use U-substitution here. So here, I'm going to say U, in this case, is going to be 2 theta. So du is going to be just 2 du, or d theta, I should say. So that'll give me a constant of 1/2 du being equal to the 1 d theta that I have in my integral. So I do need to introduce a constant of 1/2. Now, what are my new values here? When theta is equal to, what do we have? When theta is equal to 0, 2 times 0 says that u is just going to be 0. And when theta is equal to pi over 4, 2 times pi over 4, that's just going to be pi over 2. So u is equal to pi over 2. So my upper and lower bounds aren't getting switched at all. So Uh, let's see, let's go back to my blue color here. And I'm going to have my area. So if I introduce the constant of 1/2, 9 times 1/2 is just going to be 9 over 2 times the definite integral. And now in this case, we're going to go from 0 to pi over 2 cosine of u du. And now we can take the antiderivative of cosine. So I'm going to have area is equal to 9 over 2 times the antiderivative of cosine is just sine. So I have sine of u, and we're evaluating it from 0 to pi over 2. So in this case, 0 is going to give me 0, but let's go ahead and do our substitution of our upper and lower bounds. So I'm going to say 9 over 2 times sine of pi over 2. Let me clean that up a little bit. Sine of pi over 2 minus sine of 0. Well, sine of 0 in this case is just 0. And sine of pi over 2 is 1. So 1 minus 0 is, so this goes to 1. So 1 minus 0 is 1. So the area in this case is just 9 over 2, or 4.5. And there we go. So that we remember to find the interval if it's not easy to see on the graph. Substitute 0 for r and then solve for theta to identify your interval. And then once you have your interval, do your best to see how to do the integration. This one wasn't too bad. We didn't have any power reducing things like we saw in the other ones. But in this case, this next one is where things get really ornery. Find the area of the inner loop. So the area of the inner loop is just, this guy right here, okay? We're just looking for that particular area. Now, the intervals that we're going to have on this one are going to be, again, a little bit interesting, simply because the fact that we have the negative on the cosine. That's what's causing the limit to be reflected across the y-axis. Instead of opening to the right, it's opening to the left. So in this case, what I would do, similar to what I've seen before, I think, if I'm just looking at the graphs, let me get a brighter color here. If I'm just looking at the graphs from the pole, this one looks like it's going to be tangent here, but again, cosine exists only, the principal values of what your calculator would give you is only going to be in either quadrant 4 or quadrant 1. So that's what it looks like. Oh, I did that backwards, didn't I? So here, these are the two angles that we look like we're working with, but because of the nature of cosine only going to be giving us positive or numbers that are either in quadrant 1 or quadrant 4 of our unit circle, this kind of looks like it's at pi over 3, and this one could be at negative pi over 3 if we just go clockwise instead of counterclockwise. So that's what I'm going to look at here, see if my algebra agrees with what we're saying here. So like what we've done before is I'm going to substitute 0 in for r so I can figure out what the interval is going to be algebraically. So I'm going to say 2 minus 4 cosine of theta, and I'm going to solve for theta in this case. So I'm going to say negative 2 here is equal to negative 4 cosine of theta. I guess I probably should have moved the negative 4, but either way, I'm going to wind up with 1/2 being equal to cosine of theta, and the values on the unit circle that will give me a 1/2, I'm going to have theta to be equal to pi over 3 in quadrant 1. I don't know why I wrote my 1 like that. Quadrant 1, and we would have theta being equal to, and that would be 5 pi over 3 in, excuse me, and that would be in quadrant 4. And in this case, I think it's going to be easiest if we're thinking about it in terms of an upper bound to a lower bound. I think I want to use the negative coterminal angle. I do want to use the negative pi over 3. If we were all in quadrant 1, I may want to do the same thing. And when I tried looking at this one, try to use symmetry on this one, I wasn't able to get the symmetry thing to work on this one for some reason. Maybe I was just having a moment and things didn't work out for me the way that I wanted to. So I'm not going to try to do the symmetry the way that I did on the last one. But I think I'm going to use my interval on this one to be from negative pi over 3 to the positive pi over 3. That's the interval that I'm going to be working with on that one. Now, this one here, guys, part of me is torn. Do I want to show you why I want to use the calculator on this one? Probably will, just to illustrate it. But we have our interval. So again, I'm going to clear this off so I can have the space. Now I have my interval. And so let's start taking a look at this one here. This was what I was thinking about doing. Here, when actually no, I'm lying to you. The half it did work. So I'm going to use my interval from 0 to pi over 3. I'm lying to you now that I'm taking a look at the actual work that I did for it. The symmetry did work on this one. So again, we're going to say, double the 1/2. So I'm going to wind up with my area to be equal to just the definite integral from 0 to pi over 3. And then I'm going to square the expression that we have. So here 2 minus 4 cosine theta, quantity squared, d theta. Now, when I square this one, it's going to work out, it's going to come out to be really kind of interesting. And I don't want to square this one just yet. Okay. In this case, I'm going to start by looking at, I think this one's going to be easier to start with doing U-substitution. So if I look at doing U-substitution where I say U is going to be the cosine of theta, I'm going to get du to be equal to the negative sine of theta. So that means negative du is equal to positive sine of theta. And in this case, because we're going to wind up with something squared, we're going to have negative du to be equal to 1 over, because again, oh, and I forgot my d theta here, and I forgot my d theta here. What do I get? Normally what we would do at this point, we would say, well, that doesn't match. The integral doesn't match at that point, so I would normally divide by the constant. Well, in this case, I can't just divide by the constant because of the trig function that we're working with here. So what we wind up with in this case is I'm going to say negative du is equal to 1 over the square root of 1 minus u squared d theta. And I'm going to have to substitute that. I can't take that as a constant. I have to substitute that into the integrand and work with it from there. Now in this case, when theta is equal to 0, cosine of 0 is going to give me a u value to be 1. And when theta is equal to pi over 3, we're going to wind up getting a u value of 1/2. So my upper and lower bounds do switch. So we need to incorporate another negative in front of the constant. So I get one negative here, and I'm going to get another negative because of this. So the double negatives are going to cancel each other out, making it positive. So that's okay. So now let's see what my integral looks like when I start doing substitution. So we still have a positive because of the double negative situation that we had, but now I'm going from, in this case, 1/2 to 1. And we're going to have in parentheses 4, nope, not 4, 2 minus 4u quantity squared over the square root of 1 minus u squared du. So what I would do at this point is, this is where I want to actually expand the binomial that's in the numerator. And if I expand, and I'm going to have to take this because I'm going to need this space here. So if I expand the binomial in the numerator, 1/2 to 1, I'm going to wind up with 4 minus 16u plus 16u squared, all of it over the square root of 1 minus u squared du. And the only way that I can foresee trying to look at this is by breaking it up into their own respective integrals. So this is what I'm going to start looking at. I'm going to say 1/2 to 1 of 4 over 1 the square root of 1 minus u squared du minus the definite integral. Actually, let's just go ahead and take those constants out. Let's just put 1 here and put a 4 here. Let's take the negative 16 out, times the definite integral of 1/2 to 1 of 1 over, nope, not 1, I have a u there, u over the square root of 1 minus u squared du, and I take the constant of 16 out of the last one, 16 definite integral 1/2 to 1, and here I have u squared over the square root of 1 minus u squared du. And this is not at all something that I think is going to be reasonable time-wise to do on any non-calculator question on an AP test. Because trying to now do the antiderivatives of those three respective pieces is going to get really ugly and really time-consuming and really tedious. So the only reason I'm doing this is just to demonstrate why this one should be a calculator question. Okay, and we don't need to demonstrate our work to do a calculated, to calculate a definite integral on our calculator. We don't have to show our work for that. So I'm not. Here I'm going to just plug this into the calculator. I'm going to just take this guy right here. I'm going to take that part right there, and I'm going to plug that into my calculator. And I'm going to wind up with an area to be approximately equal to 2.174 square units. And that's going to take care of that problem here. Now, I really like this next question. This next question is really good. It's challenging and it's possible to do without a calculator, possibly within a time limit that you would have for first, for a multiple choice or for a question on your AP exam. But maybe not. This one is definitely doable without a calculator, but it is going to be a little bit more time consuming. Not as quite as difficult as the one that we just looked at, but definitely doable. Okay, and so let's see what we're talking about here. What this one is asking us to do, it says find the area of the region that lies inside of the circle and outside of the cardioid. So the stuff that's inside of the circle but outside of the cardioid is all of this kind of crescent shape here. That is what we're asked to identify. What is that area? Okay. So the way that we're going to do this is, first of all, we have to know where do the two pieces intersect each other at, because that's going to be what determines, or what's used to determine our interval here. So to find out where they intersect each other at, I'm going to take the two equations and set them equal to each other. So I have 3, what was it, sine of theta, and I'm going to make it equal to 1 plus sine of theta, and then we're going to just solve for theta, basically. So move the sine of theta from the right to the left, and I'm going to be 2 sine theta is equal to 1. So sine of theta is equal to 1/2. So theta would be equal to, in this case, pi over 6 in quadrant 1. And sine would be 1/2 at the angle of 5 pi over 6 also. So theta is equal to 5 pi over 6 from quadrant 2, because those are where the principal values of sine are going to come from quadrant 1 and quadrant 2, because they're dealing with positive y values. And that's going to be my interval. My interval will be from pi over 6 to 5 pi over 6. So now that I have my interval, we can start by finding out what this area is. Now this is going to be very similar to things that we have seen previously with the area contained between two curves, where we're going to subtract the part that's above the one from the bottom one. So I'm actually going to take the circle and I'm going to subtract the cardioid from it for my integral here. So my area in this case, we're going to go back to the 1/2. My definite integral is from pi over 6 to 5 pi over 6. And we're going to take the circle squared, so 3 sine of theta squared minus the cardioid squared, and I'm going to rewrite that one just a little bit. I'm going to just reverse it. Sine of theta plus 1 squared d theta. And on the outset, this one doesn't look like it's going to be something that's going to be overly complicated to try and simplify, but it's, this one does require a little bit of work if we're going to try and do everything without a calculator. Here, we're going to say pi over 6 to 5 pi over 6, and the first term squared is going to wind up being 9 times sine squared of theta. The next term squared is going to be minus sine squared theta plus 2 sine theta plus 1 d theta 1/2 pi over 6, 5 pi over 6. So when we distribute the negative, 9 minus sine squared, or 1 sine squared, will be 8 sine squared of theta minus 2 sine theta minus 1 d theta. And this is going to be kind of similar to where I was at this point on the previous problem. Okay, I'm basically at the same point where I have something that I really want to use the, ability, the properties of integrals, and we can break it up and look at each individual piece and find the integration of each individual piece and then just add them together. And that's where this one starts to get a little bit complicated, because doing that can get a little challenging. Now, when I did this one on my calculator did not give me an exact number. It gave me very close to it, but it wouldn't return the exact answer the way doing it by hand would work. So I'm going to go ahead and, for time purposes, just say that this one is doable by hand by breaking up each individual piece, but what we're going to end up with in the long run when we do our area, if you want to, I strongly encourage you to try continue working the problem out without it, and or without using a calculator. And your area is, when you do it on your calculator, I didn't get exactly pi, but if I do it by hand, I did. Excuse me. So here, what I think I'm going to do is I'm going to go ahead and just pause the video, and I'm going to just put the work here, and if you want to, you can kind of copy it down. Otherwise, you can kind of skip ahead. But okay, so here is the work if anybody is desperately needing it. The complicated bit is the first one. If I take just the 8 sine squared of theta, and I look at that one as its own definite integral, and forgive me, I got lazy with writing the definite integral of pi over 6 to 5 pi over 6. But we can take the definite integral of this one, and we're going to use the property of separating the integrals again at this point, and do U-substitution on cosine of 2 theta, but ultimately we wind up with an expression of 8 pi over 3 plus 2 radical 3. Now, the second and third pieces are much simpler to do the integrations of. Here they are in pink and kind of this grayish color. We get 2 radical 3 and a negative 2 pi over 3. So if I take those three things, now that we've done the antiderivative, now keep in mind that the original antiderivative that we were working with was still saying 1/2 of those definite integrals. So I have 8 pi over 3, 8 pi over 3 plus the 2 radical 3 for the first bit, and then we have a oh, did I make a mistake somewhere? Because those radical 3's are supposed to go away. Yep, I sure did. I just didn't write something down. This negative isn't actually supposed to be on that 2 when I worked it out, but the negative is going to be on the radical 3, so this is a negative radical 3. So we're going to say minus 2 radical 3, and then we say minus a 2 pi over 3. So you can see the 2 radical 3's are going to simplify. 8 minus 2 is going to be give me 6 pi, and 6 over 3 is going to be 2 pi, and half of 2 pi is how I was getting the area of pi overall. So that one is a little bit more complicated than some of the other problems that you may see, but it's definitely doable by hand because the more complicated integration that we would have to do is definitely doable. It's just going to be a little time consuming. This one may be, I don't want to say you'd see a question like this on a non-calculator section, but it's possible. I don't want to, make false statements without knowing, without having some kind of an absolute. But that's how we're going to be finding the area of a region for polar functions. So now let's take a look at arc length. Now, the arc length, the nice thing about these is that these almost exclusively have to be done with the calculator. So there's a lot less integration that we're going to have to look at. And I'm going to show you one problem particularly where why we want to use this stuff on a calculator. But here, the length of a polar curve, it looks similar to the formula that we saw previously for arc length. But we're going to take the definite integral of the square root, and basically we're just seeing the Pythagorean theorem over and over and over again. So let's take a look at this guy here, and we have this cardioid that we're going to be taking a look at, and this is about as simple of a cardioid as you can make. And this one is one that I want to do. I'm going to start working it out just by hand, but this one really needs to be done on a calculator. But I want to demonstrate why something like this really needs to be done on a calculator, especially if you're doing it on a time crunch. So in this case, we're given r to be 1 plus sine of theta. So that means dr d theta, the derivative of that, is going to be cosine of theta. So dr d theta squared is going to give me dr d theta squared is going to be cosine squared of theta. Not not a bad deal. R squared, because what I'm looking at is I'm looking at looking at this one here. This is the integration I'm going to do for that problem. I think it would be easier to do squaring r and then taking the derivative of r and squaring it. So r squared itself is going to be, if I take that binomial and expand it, putting it more in standard form, I'm going to have sine squared of theta plus 2 sine of theta plus 1. Now here it doesn't give us the interval, but the only way that we're finding the length of the whole thing. So the only way we can do the whole thing is if we go from 0 to 2 pi. So that's going to be our interval. So I'm going to take this, and I'm going to take this, and I'm going to substitute them into the formula that we have, where it said that, well, I'll just go back instead of writing it again. It's the definite integral from alpha to beta of the square root of r squared plus the derivative of r squared. So that's what I'm going to be substituting. Now, in this case, I'm going to take the squared terms and I'm going to write those together because those clearly are going to be something that we're going to identify as a trig identity to simplify things a little bit. So here I'm going to just say L for length, for lack of a better letter to work with here. And I'm going to say the square root of r squared plus the derivative of r squared. I'm going to say sine squared of theta plus, and here's the derivative, cosine squared of theta plus the rest of the r squared term plus 2 sine of theta plus 1 d theta. Okay, and of course here, the reason why I wanted to put those two together is because those are going to simplify to be 1 because of our trig identity. So I wind up with a 1 and a 1, so I wind up with 2 cosine, nope, not 2 cosine, 2 sine, 2 sine of theta plus 2 d theta. That doesn't seem too bad. You know, it looks like a nice little expression so far, and we can factor out the 2 and look at it like this. Oh, and I forgot to write my integral. So we're going 0 to 2 pi. I forgot to write my integral. So if I factor out the 2, I can have the square root of 2 times the square root of sine of theta plus 1 d theta. And of course, I could take the square root of 2 out as a constant, and that would give me, oh, I forgot saying I want to take it out as a constant. Write my integral thing. So square root of 2 times the definite integral of 0 to 2 pi of the square root of sine of theta plus what? D theta. So far what we've done on this looks absolutely simple. I mean, relatively speaking. But this is where things start to go off the rails. If you were to try and continue working this bit out, what we're going to have here in order to be able to complete this, you're going to need to remember some trig, but more specifically in this case, some hyperbolic identities. And this becomes excessively cumbersome at that point. And that is why we are not even going to attempt further integration at that point. And that's the reason. And again, I just want you to understand that there's a reason why, you know, we want to use a calculator on some problems. And this one, I would say, should have like a calculator symbol on it saying that we're going to be doing this integration by using a calculator. Now you can go to this first one, or you can go to this one that we have right here. But either way, when you type this into your calculator is going to give you a length of 8 units. So a couple more to take a look at here. And the next one I think is definitely something you should probably try to pause and work this one out. This one actually is finally giving us our calculator symbol. So this one we're not trying to figure anything crazy out. You just need to be able to maybe find r squared and find what the derivative of r squared is going to be, so that way you can actually use the calculator. So I would encourage you to try pausing the video and working this one out. But in this case, if we're going to say r squared, I'm going to take the expression that we have, and I'm not going to try and expand it or anything. I know I'm going to use a calculator on this. I'm going to just say 2 minus 2 cosine of theta, and I'm going to square it. Now the dr d theta, we're going to have to look at that one. So dr d theta, the derivative of r with respect to theta, in that case, that's just going to be 2 sine of theta. And if I square that, I'm literally going to just say it's this value squared. I'm not going to try to say it's going to be 2 times sine squared or 4 times sine squared theta. I'm just typing it in just like that. And again, it's asking for the length of the entire cardioid. So the only way I can have an entire cardioid is to go from 0 to 2 pi. So my interval is going to go from 0 to 2 pi times the square root of r squared, which is going to be 2 minus 2 cosine theta squared plus dr d theta squared. So I'm going to say 2 sine of theta squared d theta. And if I type that into my calculator, I get a length of 16. And one more example to take a look at, and this one is going to complicate things just a little bit because it's not giving us an interval to, or it's giving us an interval to work with, but in this case, the dr d theta is going to be a little bit more complicated here because of the way it's going to look. So I'm going to basically do the same thing that we did on the last one. Here I want to know what r squared is going to be. Well, if I take this whole thing and I square it, I'm going to just wind up with the radicand. So that's just going to be 1 plus cosine of 2 theta. And again, I'm going to definitely use a calculator on this one. 1 plus cosine of 2 theta. So dr d theta, this is where it gets a little complicated because of the square root. So dr d theta in this case is going to be, I'm going to just rewrite it with in exponent form, 1 plus 2, nope, cosine of 2 theta, not 2 cosine of theta. Cosine of 2 theta to the 1/2 power. So when I take the derivative of this, we have to take, the chain rule a couple of times. We have to take the derivative of the whole thing, the derivative of the inside part, but because of cosine of 2 theta, we have the chain rule there also. So in this case, I'm going to wind up ultimately with negative sine of 2 theta over the square root of 1 plus cosine of 2 theta. So I'm going to take that and square it for dr d theta squared. So dr d theta squared. And now I have r squared, I have my derivative of r squared. So now we can find the length, and we're definitely using a calculator for this one. So the length, in this case, they gave us the interval to be from negative pi over 2 to positive pi over 2. And I'm not going to bother trying to do anything with symmetry or anything like that with this one. I'm going to just take the numbers that they gave us because we're using a calculator. And I'm going to say the square root of r squared. So I'm going to say 1 plus 2. Nope, I keep wanting to say 2 cosine of theta, and that's not it. 1 plus cosine of 2 theta. And plus, and I'm going to put it in parentheses, the negative sine of 2 theta over the square root of 1 plus cosine of 2 theta squared d theta. I'm going to type that in my calculator, and this one gives me a length approximately equal to 4.443. And that is going to kind of wrap up all the information that we have for this presentation for area and arc length with polar coordinates. I hope this was good information for you, that you were able to get some useful practice out of it. Until next time, ladies and gentlemen, thanks for watching and take care.